We're now going to be looking at the n-queens problem. Now the n-queens problem is a classic problem in computer science, just like I said flood fill was, and essentially what it is that we have a board, and so a chessboard is 8 by 8, so we're looking at the 8 queens problem, as this Wikipedia article says, the 8 queens puzzle. And essentially what we want to do is place down 8 queens, so one queen for whatever size n is, and we want to place them down such that so a queen can move up, down, left, right. It can also move diagonally. And we basically want it to be that no queen is in the line of fire of any other queen. So in this example, we can see that this queen does not hit anything. This queen also does not hit anything. And if you look at all the 8 queens, essentially none of them overlap with each other, which means that it's solved. Now we can do this for a smaller example. So let's say 4 queens. We have a 4 by 4 board, and we essentially want to place the queens such that none of them overlap. So for instance, one attempt, I don't think this is the right solution, but I can do that, and oh, I think this is actually the solution. Cool. Because if we look at this, the queens don't overlap at all. So what we want to do is find a recursive way to basically solve this. And so once again, this is a puzzle, and it's a perfect opportunity to use backtracking. Now the way that we're going to do this is that we're basically going to try solving it column by column. So what I'm going to say is that, so in the maze solver, I could basically go in all 4 directions, and those were the different moves I can make from a given place. Now what we're going to say is that you are currently located at the 0th column. This is the column that you're at. Now, whoops, let's put a V here. So this is the column that I'm at. Now I'm going to try placing a queen at the top. Then I'm going to say, okay, let me move over to the next column. And I'm going to try placing a queen in all 4 places. And so first I'll place it here and see if it works. It didn't work. It's not valid. So then I place it 1 below. Now I try it again. It didn't work. So I go 1 below. And so this time, notice how the queens don't overlap. So now I'm like, okay, I might have a solution. So let me move to the next column. Then I try placing it in each of the rows. So I try placing it here, it doesn't work. I try placing it here, it doesn't work. Here, it doesn't work. Here, and it doesn't work because there's this queen here. So now, I ran out of possibilities. So that means that when this queen is here, none of the different rows can have a queen, which means that this original placement was probably wrong. So what I do is I backtrack and say, okay, go back to this column, take this and put it onto the next row. And then I do the same thing. So now I put the queen here, doesn't work, put it here, and I believe this works. So I move on to the next column, put it here, put it here, put it here, none of them work, so I keep backtracking and eventually trying to solve it. So this is the way, recursively, that we're going to be doing the problem. Now, first, before we talk about the code, let's first understand the actual representations that we're using. So what we're going to do is represent the board as a single list. So it's going to be board is equal to a list. And what that list represents is the location or which row the queen is at in that given column. So in this example, the first queen is at the 0th column. The queen in the first row is at the 3rd column. The queen in the 2nd column is at the 3rd row. Oh, sorry. So we're representing this board as the row at the given column. So this is the 0th element. So it's saying at the 0th column, it's in the 0th row. This is the 1st column. So it's saying at the 1st column, it's in the 3rd row. In the 2nd column, it's saying that it's at the 1st row. And if we haven't placed it yet, then it's represented by a -1. So this is how we're representing the board. So the board initially starts out as all -1s, and then we just fill it in as we go along. So we're always going to be moving in this direction and then backtracking. So for instance, in this case, I know I can't put it here, so I backtrack and try to put it in a different location. So now let's look at the actual code. So I'm going to solve it from a given column. So that column starts out at 0, and it has to keep increasing until I get to n. So in this case, I started out at 0, then I went to 1, 2, and then finally I'd get to 3. Now, That's my base case because I'm done with the puzzle. Otherwise, I essentially need to try and place the queens in each of the different rows. So I'm going to say for row in range n. So that's going to start it out at the 0th row, and then if that doesn't work out, go to the next row, which is the first row, and if that doesn't work out, go to the second row, so on and so forth. So this is the same thing where I put the queen here, then I try putting it here, then I try putting it here, then I try putting it here. So this is the actual moving in all the possible directions from Maze Solver. So I'm going to say if it's legal to put the piece in that row and in this column, then place the queen at that column in this row. Then I basically try and solve it saying, okay, move one column forward. Like we said, that basically means that if I was over here, try and solve it at the next column. Now, I'm going to take the value from solve and put it in a variable because if we do solve it, we essentially return a make 2D list of the solution because we want to go from this to this. So it's not just we're going to return true or false in this case, it actually returns a value. So I'm going to say if the solution is not equal to none, so if it actually worked when I placed the queen in this row, then that means that it worked. So now I just return the solution. Otherwise, if the solution was none, that means that when I place the queen on this given row, it means that it shouldn't actually go there because there was no way to solve it. So then I undo that move and then just loop to the next row and try to put the queen in that row for whatever given column I'm at. Then in this way, I basically keep trying to put the queen in the right row, go down the path and see if it works, and then undo the move if it didn't work. And then if I go through all the rows in this column and I can't put the queen in any of those rows, that means that there's no solution from this column given the current configuration of the board, and so I return none. So in this example, that's like if I tried to put the queen here, it didn't work. Then I keep trying to put the queen in all of these different locations. It didn't work, so I have to backtrack and say, try the next row. So this is another somewhat straightforward implementation of backtracking, except it's a little bit trickier because you have to understand the way that the board is represented, and the fact that in this case, when we loop through all of our moves, it's not that we're looping through directions, but we're looping through which row we're going to place the queen at. If we can place it because it's legal, then we place it and try to solve the rest of the board. If it doesn't work out for any of the rows, that means that we can't solve it from this column, so we return none. And that is the nqueens problem.